This is 2017-2018 Honors Geometry first period, some of the students, and we are making a webcast on some of the reasons we're going to use for proof, and I'll let the different guys introduce themselves.
Hi, I'm Matt.
I'm PT Cahill. Woo! You guys.
I'm Logan. Yeah.
I'm Wyatt. Hey, this is Zach.
All right, and we're going to get started on going over these reasons for proof. The reason we're going to look at on this page is definition of a midpoint. So if we know that B is the midpoint of segment AC, then that implies that segment AB is equal to segment BC. Now this is a definition. We like definitions to be written as biconditionals, but in order to make this work, we have to have the fact that these 3 points are collinear, or that B is between points A and C. So on the right-hand side, we'll make a little diagram, including points A, B, and C, to show that they are, in fact, collinear with each other. So if we have this right-side information, we know this is true, and that would imply that B is the midpoint of segment AC. Go ahead and slide this up a little bit so it's not fully away. Okay, next one, definition of bisect. What we're going to say in this one is that line AB bisects segment CD at point E. All right, so what that means to us is that there is a segment CD line AB is bisecting. It may be perpendicular, maybe not. We don't really know. So here's line AB. It's bisecting at a point E. And what that means to us then is that E is the midpoint of segment CD. And again, this is a definition. If E is the midpoint of CD and we have this diagram, then we know that is going to be a biconditional as well. That means that it must be the bisector, the segment bisector. Next reason is the angle addition postulate. So for this one, we're going to start with a drawing. Go ahead and use the points F, G, H, and K. So here's what our drawing looks like. There are 3 angles in this drawing right now, and I'm going to subdivide it and call these angles 1 and 2, because it's going to make it easier to identify them and to talk about them then. And what we can say with this type of drawing using the angle addition postulate is that the 2 smaller angles, measure of angle 1 plus the measure of angle 2, add up to the big entire angle, the measurement of angle FKH. Now, this is not a definition, it's just a postulate. It is not a biconditional. Angle 1 could be anywhere, angle 2 could be anywhere, and the sum of their measures still could be equal to the measure of angle FKH, so it is not biconditional. Next one, definition of supplements. Now, supplements are angles that add up to 180. Location doesn't matter. But we're going to say is that angle 5 and angle 6 are supplements. So we are told that. Using this definition, then what we could say is that the measure of angle 5 plus the measure of angle 6 equals 180 degrees. If you're told that 2 angles are supplementary, we can say they add up to 180, or going the other way, since we know that these 2 angles add up to 180 degrees, that means biconditional, they must be supplements to each other. The next one is definition of complements, which is essentially the same thing. There's just a little different. The little different part is that if 7 and 8 are complements, that means together that the measure of angle 7 plus the measure of angle 8 don't add up to 180 degrees. Instead, they add up to 90 degrees. This is another definition, and if we knew that 7 plus 8 equals 90 degrees, that they must be complementary. So this is another biconditional reason for us. Next up, linear pair postulates. So in this one, we're going to start with a drawing. I'll call these angles 9 and 10. And if we have a drawing like this, I can see that those 2 angles are adjacent to each other. Together they form a straight line. So what I can say about them then is that angles 9 and 10 are supplements. That is what our linear pair postulate says. If we wanted to get that the measure of angle 9 plus measure of angle 10 equals 180 degrees, we would first have to say this with the linear pair postulate, and then I could use the definition of supplements to say that the measure of 9 plus the measure of 10 equals 180. So it would take a couple of steps to get the sum of these being equal to 180, but that's what we have with the reasons we have. Okay, next, vertical angle theorem. I'm going to draw in two vertical angles. We have these two lines that are intersecting. Go back to calling this angle 1 and angle 2. I can see by the drawing that those two angles are vertical to each other. The definition of vertical angles isn't that beneficial to us. That would just be to say that 1 and 2 are vertical angles. It's just identifying them. Instead, we want the theorem. The theorem actually has an action to it. Using this vertical angle theorem, we could say that the measure of angle 1 is equal to the measure of angle 2. This is not a biconditional because it's not a definition. And if 1 equaled 2, they could be anywhere. They wouldn't have to be vertical angles like this one is saying. Next one we have is the congruent supplements theorem. Let's go ahead and take some space in this one. So angle 3 and angle 4 are supplements. We'll semicolon. Angle 3 and angle 5 are also supplements. Not a definition, it's a theorem. We're not looking at a biconditional this time. But what we know about this one, if 3 and 4 are supplements, that means that together they add up to 180. Likewise, 3 and 5 add up to 180. So using a transitive, we could say the measure of 3 plus the measure of 4 is equal to the measure of 3 plus the measure of 5. So these two angles add up to 180. These two angles add up to 180, so they must be equal to each other. And if we had an equation where we said that 3 plus 4 is equal to 3 plus 5, we could subtract 3 from both sides, and we'd end up with having the measure of 4 equals the measure of 5. Taking it one step further, we can even then say, using the definition of congruent angles, that angle 4 is congruent angle 5. Now, this is a theorem. It's definitely a step-saver theorem that will allow us to say certain things quicker. We don't have to use this theorem necessarily. We can write out all those reasons I said to get these angles being congruent. But if two angles, like 4 and 5, are supplementary to the same angle, angle 3, then those two angles, 4 and 5, must be congruent. Congruent complements theorem is almost the same thing. So what I'm going to do here is copy all this. Paste it down here. And what I'm going to do to change this up a little bit then is anytime it says supplements, change those to complements. Otherwise, it's the same thing. So if 3 and 4 are complements to each other, 3 and 5 are complements to each other, that means that angle 4 must be congruent to angle 5. So 3 plus 4 equals 90, 3 plus 5 equals 90. By a transitive, we could say that those sums are equal to each other. Subtract away angle 3 to get 4 equals 5, or more specifically, then angle 4 is congruent to angle 5. And next up, we have the definition of perpendicular. So for this one, we're going to say that line L is perpendicular to line M. And we want to have a drawing with this. So here is line L, and here is line M. They're perpendicular to each other. So what that means to us then is this angle right here, I'll call it angle 1, is that this angle 1 must be a right angle. And this is a definition. So what I'm going to do is include this drawing right in the middle. So if angle 1 is a right angle, we have this drawing. That means that L must be perpendicular to M. This is another one of those definitions that's going to be a biconditional. Next one, definition of a right angle. So if angle 2 is a right angle, that means that the measure of angle 2 is equal to 90 degrees. Another definition, if I told you that the measure of angle 2 is equal to 90 degrees, then that means that angle 2 must be a right angle. Next one, the right angle congruence theorem. Angle 3 is a right angle. And if angle 4 is a right angle, that implies then that measure of 3 equals 90, measure of 4 equals 90. That would be the definition of a right angle. By a transitive, we could say the measure of angle 3 equals measure of angle 4. and then using the definition of congruent angles, we could say those angles are congruent to each other. We are going to skip all those steps, use this as another step saver reason, and get all the way to saying that angle 3 is congruent to angle 4. This is the right angle congruence theorem. This is not a definition. If 3 is congruent to 4, we have no way of knowing if those were originally right angles. They wouldn't necessarily have to be, so again, not a biconditional. Last one here, definition of an angle bisector. So let's go ahead and put our drawing right here. Use the letters A, B, C, and D. I'll call those angles 1 and 2. And our given is going to be that ray BD is angle bisector of angle ABC. So if we are given that and we are including that drawing as part of the given, then what we could say using this definition of angle bisector is that the measure of angle 1 is equal to the measure of angle 2. This is another definition. So going the other way, if I know that measure of angle 1 is equal to measure of angle 2, and the drawing came from this, so that location is specific, they're adjacent angles to each other and they're equal, then I could go back the other way and say, yes, BD must be that angle bisector.